Having addressed the importance of fluctuations in observables for activated processes and the impact of the nanoscale on the size and intensity of fluctuations, we will turn our attention in this section to process timescales in which fluctuations are different from bulk fluctuations and to thermal fluctuations that are generally not accessible macroscopically in useful form. Let us return to the aspect of equilibrium and transient behavior. We found that during processes, the values of observables change in time due to driving forces given by potential gradients. At equilibrium, the gradients vanish and the values of the observables stay constant. Consider now the location of the continents as an example, as we perceive them. In our time scale, their locations are fixed. On a geological time scale, however, we find the locations to be transient in time. In other words, the time scale of the observation matters. It can influence the way we perceive an observable. As we will see next, the time of the observation window can be intimately connected to the length scale, as the values of the observables can fluctuate differently in space. Hence, we can target a particular region in space that possesses particular fluctuations over a certain time period, and so utilize the effect to design unique structured and shaped nanomaterials. This is the basis of many growth processes, resulting in specific nanoparticles, nanostructured composites, and nano-phase segregated systems. To illustrate how we can obtain unique products from nanoscale processes, let us consider a simple example in which molecules of a phase A are diffusing into phase B, and vice versa. The change over time of the concentration profile is here animated with a diffusion front x that moves proportional to the square root of time. Classical models often describe the initial phase contact as abruptly sharp and the evolution of the concentration profile symmetric. The reality is, however, far from it. The interface is diffuse and shows, in most cases, an asymmetric concentration profile that originates from local varying diffusion velocities of the species. It has been found that the concentration asymmetry can be cause for local demixing, non-stoichiometric mixing for miscible components in solid condensed phases, and bulk deviating mixing structures. Imagine on a macroscopic scale two phases in contact with an initially sharp interface. After time t, that shall exceed a critical time t star, the diffusion process leads to a lamellar binary system. We also find the lamellar structure on the nanoscale if we wait the same time. We notice in the time evolution, however, at times smaller than t star, a different binary structure due to the asymmetry of the concentration profile. Envision now we grew a mixed phase out of solution and stopped the process early, that is before the critical time t star. Or we consider ultra-thin films with combined thickness in the diffusive regime of the interface and freeze the diffusion process before we reach t star. In both cases, we would end up with unique binary phase structures that are very different from what is expected on the macro scale. Hence, nanomanufacturing of materials provides an opportunity to arrest transient behavior and with it produce unique materials. Next, we look at the possibility to extract specific fluctuations for our purpose, starting from an equilibrium situation. A visual realization of an equilibrium behavior of a liquid is the Brownian motion. Consider a particle, shown here in yellow, in a liquid that is in equilibrium. The Brownian noise manifests itself in the motion of the yellow particle that experiences collisions with the liquid molecules, whose positions thermally fluctuate. The path the particle describes is known as random walk. The question arises whether it is possible to extract on a small enough scale specific molecular fluctuations in such a fashion that the particle motion is predictable. This question is equivalent to Maxwell's demon. The demon guards the doorway of two reservoirs and lets only particles pass from right to left. This bias selection defies the second law of thermodynamics, as we ignore knowledge as a form of energy. Hence, the answer to our question is no. However, if there is a source of energy available, the idea of harvesting only specific fluctuations to direct motion is possible. This brings us to rectified thermal fluctuations in which locally available small energy sources are utilized. An example is RNA polymerase, an enzyme that translocates along a DNA strand to synthesize a new RNA strand, or kinesin that translocates along a specialized filamentous track in a cell to move loads around. In both cases, chemical energy is used towards directed binding of the enzymes in a cyclic fashion. The result is a molecular or nanomotor. Myosin is another example used, for instance, for muscle contraction. Upon close inspection, one can see that chemical processes are used to locally generate potential fields that provide the directed driving forces. Thus, although apparently in equilibrium, the system is locally in a non-equilibrated state. In this part of our lecture, that was comprised of two sections, we addressed the effect of fluctuations on properties and processes. First, we discussed the difference between equilibrated and non-equilibrated systems. We recognized the importance of driving forces that result from potential gradients. In particular, we focused on spontaneous chemical reactions in which energy fluctuations had to overcome small activation barriers. Using this statistic mechanical viewpoint, we compared the equilibrated state of macroscopic systems that possess vanishingly small fluctuations with nanoscale systems and their large fluctuations. We discussed large fluctuations and low fluctuation intensities as distinguishing features between nanoscale systems and macroscale systems. While larger fluctuations provide a sort of catalytic enabling environment, the low fluctuation density provides a control mechanism to slow reactions down. Based on this, we concluded that nanoscale confined reactions provide opportunities for environmentally friendlier, safer, and more cost-effective process operations. We addressed the aspect that processes, which are confined to the nanoscale, also exhibit time-scale different evolutions from what we expect from the macroscale. The difference in the so-called observer timescale provides vast opportunities for nanomanufacturing of products from nanoparticles to nanostructured materials. We closed our discussion by exploring the possibility of utilizing molecular fluctuations on the nanoscale to run nanomachines or motors. Imagine we could run millions of motors simultaneously, extracting thermal fluctuation energy that is otherwise useless. While on first sight this approach seems impossible because of the second law of thermodynamics, we recognize by looking at nature that only small and local energy sources are necessary to realize this dream and profit from apparent waste energy.